Thank you, thank you. Yeah, it's taken.
I can't remember. All right, so 4, 5. Which problem was that? Number 12. So she says there's a 96% probability the calculator will work. Yikes.
That's not very good.
Only got one color with me. I was hoping it'll work. All right, this is gonna be very colorful. So if she brings 2 calculators, what's the probability that she'll be able to complete her exam with a working calculator? And how do you say that? So we got to take several steps to translate this. I can work with questions like at least 1, at most 7, exactly 2. So how do I translate complete the exam with a working calculator into that type of phrase? What has to happen for her to have a working calculator? Would it be bad for her to have 2 calculators at work?
No.
That'd be fine. Or either one works, right? So she needs at least 1 to work. Once you get that phrase from what they say, and this happens all the time in statistics. We want to analyze something and we'll accept a batch if, less than this many. You got to translate what does it mean for them to accept it into math. So here, she wants to complete the exam with a working calculator. So she needs at least 1 to work. The mistake people make is they'll do this, 0.96 times 0.96, which will be less than 0.96. That's counterintuitive. Your probability should go up if you bring another calculator. You shouldn't somehow, the 2 of them together, what are you doing here? Screw you, and then they both decide not to work. That's weird. It's not going to happen. So how do I do at least 1 works?
1 minus.
Yeah.
1 minus probability. None of them work. And what's the probability that none of them works? Neither one.
0.04 squared.
0.04 times 0.04, 0.04 squared. Which will be a very small number. Then you do 1 minus that, which would be a very close to 1 number. A big probability, right? That makes more sense. If I bring 2 calculators, it should be a much higher probability that I actually finish the exam with a working calculator. One doesn't die, the other thing goes, Fred, no! Dies too. That doesn't happen. That I've ever seen. Alright. Sure why calculator's name is Fred, but that's it. Any other questions from homework? Maybe this, oh yeah.
If we turned in our homework last week, are we going to get it back soon?
Someday.
Okay. We didn't forget about it.
Maybe this will spur some questions. This Thursday we're going to have a quiz on chapter 5.
That's that's good. No, it's not. That's taking more points for us, right? It's good. Yeah, I like to get points. Hell yeah, man. Hedge against inflation. Chapter 5.
So any other questions from homework? Yeah.
5-2, number 26.
I thought might have
D.
5 to number 26.
Yeah. D.
So let me go through blah, blah, blah. So in New Jersey's Pick 4 lottery game, you pay 50 cents to select 4 numbers, such as 1, 3, 3, 2. And if your number comes up, you win and collect $27.88, of course, for whatever reason. How many different selections are possible as part A? How many different numbers can you select? And here we got to accept the fact that each ball is going to have the numbers 0 through 9 on it, right? So anything's possible from 0, 0, 0, 0 up to 9999. So how many numbers is that?
10,000.
10,000. I love it. Because it's 9,999 plus 0, 0, 0, 0. So there are 10,000 options, 10,000 different four number digits. Another way to get that is you got 4 spots. How many numbers can you have in each spot? 10 times 10 times 10 times 10. It's 10,000. Same idea. Okay, so that's part A. Part B then is what's the probability you win? How many numbers wins? Out of 10,000. There you go. Probably winning is 1 out of 10,000. So probably losing would be 9,999 out of 10,000. Exactly. All right. With me?
That's right.
This is why casinos don't care that that guy over there just won $2 million, because all these other people just lost $3 or $4, and then together they're still ahead. Who cares? Win, please. They'll bring more people in. Here, drink this. Have your judgment go down. So you owe anything? No, you don't owe me anything. You'll pay me anyway. If you win, what's your net profit? What do they mean by that? You're going to win $27.88. What the hell's up with that? You actually made how much money then? $27.87.50, because you had to pay 50 cents to get in there. How are we doing? So the net profit would be $27.87.50. Now part D is the one that is the shortest question with the most work, right? You can find expected value very easily if you have it set up like this, right? Because then you just make your XP of X and go from there. And this, of course, is going to be the heart of this quiz on Thursday. I gave you that handout that's got the worked out side, and on the back was the blank one we did together in class. You can expect the quiz to be very much like that. Right? Very nuts and bolts. So how many options are there here? How many outcomes are there? 2. You win or you lose. So if you win, how much money do you make? $27.87.50, right? If you lose, negative 50 cents. Not 0, you're out the 50 cents, right? How are we doing so far? Definitely got to be negative, because it's not flowing in your direction, it's flowing away from you. Okay, how are we doing so far? I mean, this is, what we're doing is we're taking a situation and putting it into this form. Because we can. There's a probability associated with each of these, isn't there? What's probability of winning?
1 out of 10,000.
1 out of 10,000. Probably losing? The rest. So sure, they got to pay out this much money to somebody, but they get 50 cents from this many people. If they're smart, they're going to more than offset the amount of money they're going to pay out, right? That's the idea. Which is why it's sometimes called a tax on stupid people. Because the state's making money. So how do I find the average? The expected value. What's the formula for that?
X squared dx.
Expected value. The first 3 letters are what you need to get started, right? Expected value, also known as the mean. What's the formula for that?
X dx.
Okay. Starting to get very worried. That should be, that's not as good as NP for binomial, but that's still pretty damn nice of an equation. EXP, expected value. Crazy. So I need, of course, I need the X, P of X column here. So now you just multiply, cross, add down, there you get your expected value. So I'll let you guys finish that out. I'm tired of doing the work for you.
Like that, yeah.
Yeah. So here's what expected value really means. They say in part E, if you bet 50 cents in an Illinois game, the expected value is negative 25 cents. What does that really mean? On average, every time you play the game, you lose 25 cents. So if you play the game 100 times, on average, you're going to lose 100 times 25 cents, which is 25 bucks. Right? That's what that means. So probabilities really only make physical sense when you're talking about a large collection of trials. If I flip a coin once, what the hell does 50-50 mean? It doesn't mean a damn thing. Is it going to waver on it? No, I don't know. It's just over a large period of time. If I do it 1,000 times, I expect 500 heads. That's when the probability really starts to make sense. So what does expected value mean? It's an average. If I play this game a lot, 100 times, I can expect to lose $25 on average, right, for every 100 times I play. Or if 1,000 people play, they'll all lose $250, right, together. You with me? A little bit. So if somebody else's expected value is negative 18 cents, which one is better for you to play?
The negative 18 cents.
The negative 18 cents, because on average you're losing less money. You're still losing, which is funny. But it's still relatively better. You're losing less money. Okay, maybe. So in a casino, you got all kinds of people in the casino playing games. If the expected value on one game is negative 10 cents, that doesn't seem like a lot, but you multiply it by all the people that play the game, and the casino's making a lot of money off of this. The one guy wins, but who cares? 8,000 other people lost earlier that day, so they don't care. That's why they give out free drinks. Why not? Yeah.
I heard another thing that made sense to me about casinos, in that you'll never get ahead of a casino because the casino only needs to bring you to zero once to be ahead, and you're never going to bring them to zero, sort of thing.
True. All right. I don't care. I just want to bring myself to some other number than zero. But yeah, you're right. But then you just think about all the people that come there.
Yeah.
And they're all kind of working towards zero.
Oh yeah.
The casino's just like, yeah. That's why I love that one movie where they said, why don't you just mail your money in, save some airfare? Lose that much money anyway. Okay. That was a year living dangerously. Johnny Dangerous. Michael Keaton movie. Any other questions from chapter 5 before we get back into 6 yet?
The same section back to 19 to 29.
So that one's really, I like 29 because it's a more real life problem. I mean, how insurance companies actually set their premiums are basically like this. You can imagine that it's a little more complicated than this, but it's basically this process. Let's see, is my green really that bad? Okay, look at that. 29 is a 0.9986 probability that some randomly selected 30-year-old male lives through the year. Let's see, blah, blah, blah. A Fidelity life insurance company charges $161 for insuring that male. Will live through the year. If the male does not survive the year, the policy pays out $100,000. And now you start to see how insurance companies operate, right? They are completely beholden to the probabilities. That's why when you turn 25, they've done probabilities based on age ranges. And they found that the probability of being in a crash of over 25 to something is less. So then your premiums go down because they're not going to expect to pay out so much for your age range. Does that make sense? I mean, and of course they do it geographically. If you move, like I just did, your premiums change a little bit. They went up for some reason. People don't know how to drive where I live now or something. You with me? So they do it all based on all these different variables. This is really just breaking it down to live or die. Cool. So from the perspective of the 30-year-old male, What are the values corresponding to the two events of surviving and not surviving? Just kind of set it up. Live, die. So if this dude lives, is cash flowing in or out from him? Out, because he's got to pay it, right? How much does he have to pay? So it'll be, what would I write here? Minus 161. He's got to pay $161 out. If he dies, how much money comes into his estate?
100,000 minus 161.
Well, 100,000. I don't know if they have to do minus 161. I don't know if that's the point here. Yeah. Policy pays out $100,000. Yeah. Okay. So minus 161 would be what?
99839.
Thank you. Cool. So it's a lot like that lottery problem we just did a minute ago, where the 161 is what you got to pay to get in, and then this is like your net profit. This is talking about a dude dying, but still it's the amount of money that his estate makes. There's a probability associated with each. All that part B needs is this. This is part B. What are the values associated with each? You with me? So there are two possible outcomes. You can live or you can die. What are the values associated with those two outcomes? Negative 161 and $99,839. Those are the two values. Okay. Now part C is probably, can the insurance, oh, part B. I'm sorry, this is part A. Part B now is finish this thing out. What is the probability that this dude lives? 0.9986. What's probably that he dies?
10014.
0014, yeah. And then how do you find the expected value then?
Just multiply them.
Multiply across,
And then
add down. Right? Get that XP of X, multiply across, add down. If you can set up that XP of X table, the math is easy from there. Multiply across, add down, there's your expected value. So whatever the hell you get once you do that. From the guy's perspective, this should definitely come out to be negative or positive. Negative, because the insurance company then would be getting that money. They want to make a profit. So they always figure out what's the probability I got to pay out this much, and then they set their premium a little higher than it has to be so they can insure to make a profit. And then part C says, well, there you go. Can the insurance company expect to make a profit from selling a lot of these? If it comes out negative, they will. Because this is from whose perspective?
the guys.
That's his expected value. So if his expected value is negative, why is it negative? Because that money is going to the insurance company, right? So if this comes out negative, the insurance company is going to make that money. So they will make a profit. If it doesn't come out negative, the insurance company is stupid. Sign up with them anyway because you can get a decent price for your life insurance. Do you guys kind of see what I'm saying? So it's sometimes it's called a fair game when it comes out to be zero, because then neither party expects to make money over the long run. It's a fair game, but no games are fair. Whoever set up the game is going to actually put it in their favor, obviously. Whoever has the goal makes the rules. That's the golden rule. Any other questions? You're learning very strange things in this class now. Any other questions from chapter 5? Okay, good, because I want to devote a big chunk of the day to the basics of the first couple sections in 6. So, here's the idea with 6, and I've got a little handout we're going to work on together, or you guys are going to work on together. So somebody remind me, for a normal curve, within one standard deviation, what percent do you expect to find? 68%. And again, this is roughly 68%. Within 2? 95. Within 3? Careful now. 99.7. Now, this is good if the values we're looking at happen to be exactly 1, 2, or 3 standard deviations away. But very easily that won't happen, right? So something that is normally distributed, that's kind of lame, but I don't care, just to get us into this section, something easy, are IQ scores. IQ scores are actually normal because we force them to be, but let's just go with it. IQ scores have a mean of 100 and a standard deviation of 15, and they are normally distributed. So let me start us off with a question we can answer without Chapter 6's help, and then a question that we desperately need Chapter 6's help. So, number 1, what's the probability somebody has an IQ higher than 130? Try to draw that picture out. This is exactly like the question that was on the first test. Almost 2.5%. So if we draw this out, what goes right in the middle? 100. This would be 115, this would be 130, right? So I'm looking for this area right there. Cool? I'm looking for that area right there. That'll be the probability. That's exactly 2 steps up. Empirical rule says that within 2 steps, there's how much? 95%, right? So how much is going to be outside? 5%. So how much is on this side? 2.5%. So that's the usefulness of the empirical rule. Now think about what that means. If you wanted to set up a club and you wanted only 2.5% of the population to be eligible to join, you could say, well, your IQ's got to be higher than 130. And right there, you know, you're guaranteed, and trust me on this, this is true, IQ scores are normally distributed. There are about 2.5% of the population that has an IQ of higher than 130. You with me so far? On one level, that's kind of cool. All you got to know is that it's normal or close enough to normal, which is a question we'll investigate in this class. When is it close enough to normal? Let's go with this. This is actually normal, and I can do all these probabilities. I'm guaranteed if I set the mark at 130, then only 2.5% of the population could even apply. Right? There is a group like that. They actually set it at 133. Anybody know who that is?
Mensa.
Mensa. So they set it at 133. They didn't even like the 2.5. Wasn't letting in too much of the riffraff. We got to set it at the 133, and now it's even a lower. So that is going to be my. That'll be my example for something that the empirical rule lets us down on. What's the probability that x is greater than 133? Here's my 100. Here's my 133. Need that area right there. Can somebody tell me, where'd that 2 come from that I put down there? 2 standard deviations. So this would be 1. This would be 0. Right? The mean is always a z-score of 0. I just gave away what I was going to say next. How do I get this guy's number here? Then I calculate his z-score. So take a second and figure out his z-score. 2.2. Or take less than a second. So how do you get the z-score of something? What's the formula?
It's x minus mean over standard deviation.
Yeah, so it's how many steps fit into how far I've got to go, right? That's why the z-score is the number of standard deviations, because it is how many steps fit into that. So in this case, it'll be my data point of 133 minus the mean divided by standard deviation, 33 divided by 15, 2.2. Does the empirical rule say a damn thing about 2.2 steps? No. So the empirical rule obviously is useful, but it immediately becomes something that I can't really use in general, because very few things are going to come out to be a perfect 1, 2, or 3, or negative 1, 2, 3. You guys with me? So what we use is a chart. And again, look on page 238. 238, you see that green box? We put it up here just so I can shock them all. Who's talking about Winnie the Pooh? There's a honey pot from Winnie the Pooh up here.
Ooh.
That is random.
Kinda narrative.
Really?
I have a class here at night.
That is funny. That's obviously a sign. Field trip. Shoot, of course I do the same thing I always do. So everybody's got this here now? Somebody, can you do the one that says whiteboard? Thank you. It should be a little better. So if you look in the very back of your book, very back page, that's the chart that we're going to be addressing, we're going to be looking at for a bulk of the rest of the semester. So you're going to become very familiar with that thing. Okay. So if you look, this is the equation. For a normal curve, that's the equation. That's my finger. That's the equation for a normal curve. With me? Do we want to use that equation directly?
No.
In fact, we can't. There are a few of you who can. If you've had calculus, what calculus does, one of the two things that you do, is you learn how to calculate the area under some freaky shape. So remember that handout we did last time, and I really want to make this point. The probability was exactly the same as the area of what I was looking for, right? So if I can find the area of where I'm looking for, if I can find this area, and truly the area, I've got the answer. That'll be the probability of getting there. Because the whole area is 1. So I could use calculus to find the area using this beautiful formula, which we never have to look at again. Or I can let some calculus person do all the work for me and just collect it all in a table. And that's what we're going to do for this class. So holy shit, this is a lot of stuff going on here, right? Let me see if we can read this correctly. So let's capture something we should already know. If there's 2.5% up here, how much should be below this? 2.5% up here, how much should be below it? 97.5, right? 0.975 is a decimal. You with me? So watch what you get when you look up z of 2.00. 2.00. Don't you get really close to 97.5? You get not quite exactly right. So this has got the empirical rule in it. The empirical rule is in here. It's just that it now fills in a lot of gaps. Now here's how you read this. If I wanted a z-score of 1.78, I'll go to 1.7. Second decimal is 8. 1.78. There it would be right there. There'd be that area below 1.78. So whenever you look up a z-score in this chart, I'm talking really slow, this must be a note. Whenever you look up a z-score in this chart, it tells you the area below that z-score. That is crazy important. Because sometimes you want the area above. Sometimes you want the area between two things. So you got to know how to kind of adjust it from what you see. For example, in this case, we want the area how related to 2.2? Above. So if I look up 2.2 here, what do we get? 2.20, right? We want exactly 2.2. So 2.20 is 9861. So on my picture, which I have conveniently hidden, this is what I want to see from you guys. This is what you do for yourself to make it easier on yourself. You shade in the area you want. You calculate the z-score, because how far away it is determines how much area is below it. The further you are away, the more area there is below you. Does that make sense? Or the further you are actually to the right. So where do you put the 0.9861? Where is that on the picture?
The rest of it.
It's the area below. That's 0.9861. So how do I get my answer then? 1 minus that. It must be the rest. It must be the other side. What is 1 minus 0.9861?
0.0139.
I like it.
So they want the top 1%. Basically the difference.
Yeah, just a little over the top 1%, exactly. No, it wouldn't be. Because again, this is very specific. This always tells you the area below. So to get the area above, I just do 1 minus. Why did I have to cut in half the one from the empirical rule? Because the empirical rule is all about in between two. So if I do 1 minus, I get both sides. If I want only one side, I got to cut it in half. The math is not intensive here. The concept gets a little intense sometimes. Right? Let's do a couple more just to see if we can use this chart correctly. And this is what I'm going to be using. I will show you how to do some of the stuff in the calculator, but I like using the chart because it really gets you focused on how the probabilities change as you move around. So let's do another problem. Let's do one a little more direct. Can you find the probability that a z-score is less than 3.01? Don't say it out loud. Again, it's in the very back of your book. So what do you guys get? Yeah, cool. Because if you look at 3.00, so 3.01, 0.9987. Now notice how much are they changing up here? They're not changing by much at all. How much are they changing like way up there? Quite a bit. Because how much stuff is out here? Not much. So if I take one little step, how much more have I gained? Not much. In the middle, it's going to be changing a lot, because where's most of the stuff? In the middle. So the probabilities are changing a lot up there, not very much at all down here, because you're not picking up a lot of stuff in that little tiny tail. How are we doing so far? Semi-decent. I like that. Somebody see anything going? Yep.
So if we were to go back the opposite direction with the z-score, would it be negative? And that's why we don't consider the...
No. So let's do a problem now. I've sort of been focusing on the positive side just to get the idea down. Area can't be negative. Probabilities can't be negative.
Yeah, but I'm saying if the z-score was like all the way to the left, then the z-score would be negative.
The z-score would be negative.
Okay, and that's why.
And the area would be small underneath it, yeah. So this came out to be I forgot already. 987. So try this. What's the probability that z is less than negative 1.98? You'll notice something very quickly. This is a positive z-score chart. So you need the negative z-score chart, which is just on the other side. So again, it's the very back of your book. Try to find negative 1.98.
Yeah, keep reading.
Yep. You should be getting 0.0239, 2.39%. See, keep doing this. How about something that's a little bit different? What do you think you do with this here? The probability that negative 2.07 is less than z, which is less than 1.14. Draw that first. The people that don't draw the picture are the people that will more likely make mistakes. If you draw the picture, it will keep you focused on what you're trying to find. Draw this picture. Since it's z-scores, what goes right in the middle? Zero. I love it. The mean in z-scores is 0. Not sure if I have enough of these. So let me first, anybody not have their book with them today or don't have the... Okay, so... So what does this look like when you graph this thing? So right in the middle, of course, like we said, is 0. Negative 2.07 is somewhere over there. 1.14 is somewhere over there. So the area that you want is there, right, in between those two. How do you think you get that? If you look up 1.14, what area do you get? 1.14. 1.14. 0.8729. Yeah, 1.14, 8729. That, of course, goes from here all the way down. So that's obviously too much. How much too much? Exactly this much too much, right? If I could just subtract this much off, won't I only have the area in there? So obviously, if they ask you a question about between two things, you find both areas and subtract. Do not subtract the z-scores. What happens if you subtract z-scores? Are you in the right place? Z-scores are where the hell you are. You change those, you change where you are, you change the question, you're screwed. Don't do that. Don't give me negative answers. Probability can't be negative. Area can't be negative. It can't be negative. So don't subtract the wrong way. Big minus small. All right? So what's this area here? Negative 2.07. Negative 2.07.
0.0192.
0192. Why? That's a little better. 0.0192. So how do I get my probability answer? What do I do to get this answer? Subtract them. So 0.8729 minus 0.0192 is whatever the hell. 0.8537?
Yeah.
Sweet. Yes, sir.
You can technically just use one of the charts, right? Well, if you know it, like if you know for the, like I know if you take the same number and it's minus side one hand, it's negative.
There's a shortcut that I'm not going to talk about yet. Because shortcuts are always getting away from the concept a little bit. So we'll see if anybody picks up on the shortcut. So here's what I want you guys to do. And some of these you might need some help on. So some of them I haven't directly addressed. I want to see if you guys are able to do it. Please work together on this. If you really don't like other people to work alone, it's fine. Yeah, that's bad. But it's hard when you haven't done any calculus. So.
So it's not too easy.
Oh yeah, because you get the negative x squared. Yes. But you can attack that with series. Right.
Are you serious?
No.
Great.
You must. But for like tricks in the textbook. Oh yeah.
From what I can figure, we just, since that's the z-squared, it's squared now, because 0 is always,
If anybody else wants to borrow a z-score chart, they'll be up here. If you want to keep it, you must bring it with you to a test or a quiz, because I'll only have so many other ones to give out. Please do that for me.
yeah, you gotta shade it. So yeah, I'll show you that. Depends on what way you go.